Hi, welcome back to McClutchy Maths. My name is Natalie McClutchy and today I'm going to be taking you through a new video series. And in this video we're looking at an introduction to arithmetic sequences. In this particular video you're going to find out what an arithmetic sequence is. We're going to talk about how to prove that a sequence of numbers is arithmetic. We're going to talk about writing recurrence relations and what that is, and then also how to use recursion to find our first 5 terms of a series. Then we're going to look at a general rule for an arithmetic sequence, followed by how to use the iterative function on our calculators to find the nth term. We're going to graph an arithmetic sequence and then talk about what's coming up in the rest of this video series. So you can see this particular one is jam-packed, but it's not overly difficult. So hopefully you can stay with me for the whole video and we can get through a lot of content. This particular video is aimed at a lot of different types of students in Year 12 General Maths in Queensland, Victoria and Tasmania. If you're doing maths applications in Western Australia, thanks for joining us. And if you're doing math methods, this is part of the Year 11 syllabus in Queensland and Western Australia. So let's kick right off and talk about what an arithmetic sequence is. It sounds like something very scary, lots of big words there, lots of letters, but it's not really a big deal at all. It's just a series of numbers that increase or decrease by a fixed quantity. So that fixed quantity could be a series of numbers that goes up in twos. For example, this one here, 2, 4, 6, 8, 10, all going up in twos. Or it could go up with another whole number, 5, 10, 15, 20, 25. That one's going up in fives. We can even have one that decreases by a fixed quantity. We're starting here at 1,000, going down in 100s, 1,900 and so on. Now, it doesn't have to be whole numbers. It could be going up by a decimal amount or decreasing by a decimal amount as well, or by a fraction. It might be presented to you in that way too. Now, something very important to notice is that the difference between two consecutive numbers is the same. So with our series that was 2, 4, 6, 8, the difference between 2 and 4, they're consecutive numbers, which means they're side by side. Well, the difference between those was 2, and the difference between 4 and 6 was also 2. So that difference stays the same all the way into infinity. And we call that difference between those two numbers the common difference, and it's represented by the letter D. Now that's just something important to remember, because whenever we're talking about arithmetic series, we're going to talk about the common difference. We've also got some naming conventions in our arithmetic sequences. Every term is given different and special notation. So the first term is called T1. Now you can see the 1 is a little number, smaller than the letter T, and it sits down slightly lower, kind of like a power, but in the opposite direction. Now, it's important to note that that doesn't mean that that number 1 is doing anything to the term. It's not raising it to a power, it's not multiplying it by 1, it's not adding 1 to it. It just means simply it's the first term. It's a naming convention. And we follow that naming convention all the way into infinity. So the second term would be called T with a little 2. That's called a subscript. And all the way into infinity, our nth term, which is one that we haven't defined yet. It could be the 100th term, it could be the 18th, 100th term. We call that T with a little subscript of n. So very important that you don't write that subscript the same size as the letter T, because then it changes from being a naming convention into something different in algebra. Okay, so let's look at a few little worked examples now, the things you might have to do with arithmetic sequences. So firstly, we've got to prove or show that the following sequence is arithmetic. So they've told us that it is, we've just got to show that we know how to prove it. So the first thing we're going to do is recognize that if this is an arithmetic sequence, then the second term take away the first term will be equal to the third term take away the second term, and the fourth term take away the third term, and so on, all the way into infinity, and it's all going to be equal to D, the common difference. As we can see just looking at it, we can see it's going up in 3, so we know that our common difference is going to be 3, but we have to prove that on paper. So firstly, here's term 1, here's term 2, term 3, and term 4. So once again, using those little naming conventions with the subscripts. Okay, so we now need to ask ourselves, does 5 take away 2 equal 8 take away 5 equal 11 take away 8? Well, we know that it does. We're told it's arithmetic. So we're going to prove that the difference between all of those is 3. And so yes, it is an arithmetic sequence, D equals 3. Now, the way I've set this out was purely for the purposes of showing you how to do it. Let's have a look at it, how we would do it with some proper working. So firstly, we write this statement, T2 minus T1 equals T3 minus T2 equals T4 minus T3. And if you were asked to prove it using more terms, you could just simply follow that pattern out. And that's all going to be equal to D, the common difference. So now we simply substitute into the little algebraic sentence that we've created, and we've got 3 equals 3 equals 3. Therefore, it is an arithmetic sequence, and the common difference is 3. So we've proved it. It didn't ask us to tell us what the common difference is, but by definition, it has to have a common difference for it to be an arithmetic sequence, and that's why we've put that as part of our proof statement. Let's talk about writing what's called a recurrence relation. Now, this is very important for us to know the difference between a recurrence relation and a general rule for sequences. You might be thinking, what is recurrence? You'll also see it called recursion. Well, it's simply a type of equation that defines what our sequence is doing based on a rule that gives us what the next term is going to be as a result of what we've done to the previous term, called a function. Now, that might sound very wordy and mouthfully. Let's talk about what that actually means. It's a way of communicating, basically, lots of key information about our sequence, such as what the common difference is and what the first term is. And for arithmetic sequences and geometric sequences, in fact, we usually set up recurrence relations in this particular form. Now, I'll get to what's in the orange box in a moment, but let's just unpack from left to right what we see on our screen. Firstly, it tells us T1 is equal to the letter A. Now, when we actually write our recurrence relation, you actually replace the letter A with whatever our first term is. So your first term might be 1, it might be 1,000, it might be negative 53. Whatever A is, that first term, you just simply write that into the recurrence relation and replace the letter A. So it tells us firstly what the first term is. That's very important for us to know how to find, for example, the 100th term if we know where our starting place is. You'll notice there's a comma. So recurrence relations always start with the first term is this, comma, and then they tell us what's happening inside the sequence. So it tells us, if we go to the right-hand side of that equals sign, that whatever we do with a particular term, it might be the 15th term or the 38th term, the nth term we're calling it, a random term, and inside that box is something that we do to it. So we might add a common difference to it, we might take a common difference away, we might multiply it or divide it by something if we're using geometric sequences, which we'll talk about in a few videos' time. So I've put that orange box there just to show you that we do some sort of operation in there to the term, and then it becomes the next term, and that's what's on the left-hand side. So let's say that n was equal to 3. We're talking about the third term here. We do something to it and it becomes the fourth term, 3 plus 1, which is what the Tn plus 1 is. Now, it might sound a little bit confusing, but once we start substituting some numbers in there, it'll make a lot more sense. So we've got this first term, and then we've got this second part, which is what's on the right-hand side of our equal sign, and then we've got that third part there, which creates our final term. So anytime you're asked to write a recurrence relation, just remember there's 3 parts to it. Term 1, and then an equation. Okay, so an arithmetic sequence is always going to be following this type of form. We've still got that T1 equals A, remains the same. And then you'll notice what was in the orange box has been replaced by a plus D. It's plus the common difference. Now, sometimes common difference could be a negative. That's okay, because when you plus minus, it becomes just a subtraction. Okay, so this is something you must memorize, this kind of form of an arithmetic sequence. You won't find this on a formula sheet if you're in Queensland or other states. So this is something that you need to know. And if you're asked to write the recurrence relation, this is the form you must put it in, not the general rule off your formula sheet. Okay, so let's have a little look now with some numbers in it, and this will make a bit more sense for you now. When I see something, and this is presented to me, this is what the recurrence relation looks like when it's got numbers in it. So what that's telling me is that my first term is 15, T1, and that I've got an arithmetic sequence going up in 8s. So all that's telling me is if I know what the 10th term is, T10, I add 8 to that and I get T11, which is term 10 plus 1. Okay, we're going to do that now with this particular worked example. A sequence has a common difference of minus 2 and the first term is 11. We need to write the recurrence relation for the sequence first. So we've got all the key information that we need. So firstly, we're going to write down what its basic form is going to look like. This is the one you had to memorize. And then we're simply going to substitute. We know that our first term was 11, so A is replaced by 11. We know our common difference is minus 2, so that replaces the letter D, and we've now written our recurrence relation. It is that simple. Okay, now we've got to take that recurrence relation that we wrote and generate the first 5 terms of our sequence using that recurrence relation. So simply what we're going to do now, we know that the second term is going to be equal to the first term, take away 2. So we're going to put our first term in, which is 11, take 2 away and we get 9. So we've got the second term in our series. We're going to do the exact same thing. Now we know that the second term was 9, so we take 2 away from that to generate our third term, and our third term is 7. And we're just simply going to repeat that process a few times until we get our fourth and fifth terms. So our series will then look like, it'll be first term 11, 9, 7, 5, and 3. So we just write that down at the end as a statement. It's always important to make sure we just summarize what we've been asked to do. Okay, now, if you're in Queensland, you're very lucky because they give you the general rule for the arithmetic sequence on your formula sheet. You'll need to check your formula sheet if you're in other states. So it looks like this. We've got the nth term is equal to the first term plus n minus 1 times d. Now the reason why we would use the general rule is because it will help us to find any term we want all the way into infinity without having to generate every individual term beforehand. That's the unfortunate thing about using recurrence. You need to know the term before to generate the next term. Whereas with this arithmetic sequence rule, we can get the 50th term or the millionth term. We just simply have to substitute the information in. For example, if I needed to find the 50th term, I would take the first term and then I would add 50, take away 1, which is 49, and I multiply the 49 by d. Now this is the important bit. Some students get their order of operations a little bit confused. So what they might do in this situation is take T1 and add 49 to it and then times the result by the common difference, and that's a big no-no. The 49, which is the 49th term, gets multiplied by the common difference, and then we add the first term back to that. So let's see how this works with an example. We've got a sequence with a common difference of 4.5, and the first term is 8. Find the 23rd term. So we start by writing our general rule. Now you might be thinking, well, how do I know what to use? Do I use the recurrence one, or do I use the general rule one in a situation like this? I'm a bit confused which one I use. Well, you only really use the recursion if you need to find the next term or the first 5 terms. Whereas in this situation, we want to find the 23rd term. We don't want to find all the 22 all the way up to the 23rd. That would be very tedious and painful. So that's when we use our general rule. So recursion is really only useful if you've got one term and you're asked to find the next term. Okay, so I'm going to substitute in the information that I have. I know my first term is 8, so I replace T1 with 8. I know my common difference was 4.5, so I replace D with 4.5. And I'm going to be replacing the letter N with 23, because that's what I'm trying to find, the 23rd term. So let's simplify that a little bit further. I've now got 8 plus 22 multiplied by 4.5. So I need to do that part first on my calculator, and then add the 8 to it, and I'll get the number 107. That's my 23rd term. So using the rule can be very handy because you can very quickly find any term in that whole series just with 2 pieces of information, first term and the common difference. Okay, we're now going to do something called the iterative function on a calculator. This is a quick way to generate all of the different numbers in a sequence. Now, finding the rule, definitely faster for things that are a long way into the future, but this is also a quick way to do things very quickly as well. So we're wanting to find the 12th term where the first term is 18 and the common difference is negative 0.2. So this is a good way to also check your work if you've used the rule. So the first thing you're going to do is put your first term into the calculator. So we're going to type in the number 18. Now it's very important we press the equals button. Notice that will drop it down to the bottom of your screen. Now if you're not using a Casio calculator, you're going to be able to do the same things on your calculator, but it might work just slightly differently. So just have a little play around and see how that works on yours. But you definitely have to enter it first to be able to start using iteration on the calculator. Okay, so now what we're doing is we're taking 0.2 away. So I'm going to type in minus 0.2. Now remember, I've already put the first term in. So when I press the equals button, I'm going to find the second term. So second term. And each time I press the calculator's equals button, I'm going to find the next term in the series. So here's my third term, fourth term, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. So I can actually do that really quickly on the calculator. And this is a good way to find out, for example, if you're asked when does the series get below 0, or how long does it take for the series to reach a certain figure. So we're going to do more of those kinds of questions when we get particularly into some of our complex problems in future video series. And that's how to do it on the calculator with the iterative function. Now let's just talk very briefly about how to graph an arithmetic sequence. I know you all know how to do graphing. By now you should do, because you're in senior years of school. So I'm just going to show you what an arithmetic sequence looks like on a graph. So I've got the first 5 terms of a sequence, and this one's going up in 5s, 5, 10, 15, 20, 25. So we could very easily graph that, and we would see that we're actually forming a straight line. And that's something very important to note. Arithmetic sequences always form straight lines. Now you notice that this went up in 5s, and that was our common difference of D. Something important to note is that the gradient of a straight line is equal to the common difference. We're rising 5 and we're running 1. So for every term that we increase by 1, we're actually going up in 5s. And that's where we get our gradient from. So if you're ever given a situation in an exam where you've got a graph where you see straight line increase or straight line decrease, you know that it's following an arithmetic sequence. And we can see straight off that graph what our first term is, and using the gradient we can find the common difference. Let's have a quick talk about what's coming up in our future video series. We're going to be looking at our simultaneous equations in our next video. That will help us to find what our first term is and our common difference is if we're given information about 2 numbers later in the series. So that's kind of a little bit more complex work there. We're also going to look at some different types of applications of arithmetic sequences. I'm going to have a video on simple interest, a video on depreciation, and a video on population growth, and perhaps some extra videos on some complex questions from past exam papers. Then we're going to talk about the sum of an arithmetic sequence, and this applies to our students doing math methods. It's slightly more complex work. And then we're going to jump into a little mini series on geometric sequences. I'd like to also welcome some of our new subscribers this month. We've had a lot more than 4, but these are the ones who've shared their names with us. Thank you so much for joining us here on the channel. And why not follow us also on Facebook? McClutchy Maths often has little fun jokes and little fun tips and tricks. And also we do share whenever we're releasing new videos. You can also contact us at our email address if you've got any questions or would like to offer some advice for the next video series. So once again, thank you very much for joining me here at McClutchy Maths. I'm Natalie McClutchy. Have a wonderful day.